Okay, this is example number 3 from 5.2. We're going to end up using our properties of integrals to evaluate this function. So it asks us to integrate negative x squared plus 4x minus 3 from 1 to 3. What it's really asking us to do is find the area underneath the curve from 1 to 3. And not by using Riemann sums, not by using rectangles, but finding the exact area. Okay, so if we can't separate it into perfect geometric shapes, then we need to make sure that we know those properties of integrals so that we can find the exact area underneath the curve. Okay, it gave us some additional information as well. And so thinking back to our properties of integrals, do you notice that I have 3 different terms here? One of the properties says that I should be able to take each of those and separate them as long as they're only separated by a plus or minus sign. So that's what I did first. I took the first term and I made my own integral. I made my second term, I made my own integral, and I took my third term and I made my own integral. I can do each of them separately from 1 to 3, and that would be the same as doing them all together. I'm then going to use the rule in my properties of integrals to take out those coefficients. If there's a number in front, I should be able to just take it out and put it up in front. And so that's what I did for this first piece. You notice that there's a -1 as a coefficient. I'm going to bring that -1 up, and then I just have the rest of my integral. In the second piece, I have a 4. I'm going to bring that 4 out, and then I have the rest of my integral. And for this last piece, I'm going to take out the 3, and then I have the rest of my integral. In the problem, because I don't actually have a picture and I can't find the exact area, they gave us a few other pieces of information. Didn't it tell us in the problem that the integral from 1 to 3 of x squared was 26 over 3? So that's where I got this 26 over 3 from. And remember, there was a negative out in front, a -1 out in front. It also told me in the problem that the integral from 1 to 3 of x is 4, right? And don't forget that you had a 4 out in front, so that's where that 4 came from. And then I can do the last piece that says that the integral from 1 to 3 of 1 dx is 2, and then don't forget you have the -3. So I can use my properties of integrals to separate, to take out my leading coefficient or my coefficients there, and then I can use the information that they gave me to figure out what each of those values are, what the exact area underneath each of those curves are. I can then add them together using my properties of integrals again and say that the area underneath the curve of my original problem from 1 to 3 is really 4/3. Okay, so using my properties of integrals to separate it into little pieces and still evaluate without a picture. Okay, look at example number 4 with me. It says here, if it is known that the integral from 0 to 10 of a function is 17, meaning the area underneath the curve from 0 to 10, this whole thing is 17, and the area underneath the curve from 0 to 8 is 12, this little piece is 12, can we fit, no, I'm sorry, the other piece is 12. From 0 to 8 is 12, sorry. Then can we figure out what the area underneath the curve, or the integral, from 8 to 10 is? Well, if the whole thing is 17, and this little part is 12, then what would be the rest of it? Well, could I do 17 minus 12 to get the difference, the area from 8 to 10? So I can say that the integral of f of x from 8 to 10 is really 5. Without a picture, without doing a whole bunch of rectangles, as long as I know those 2 little pieces, I can find the missing piece using my properties of integrals.